Hey guys, this is Robbie Avis with RPP. I want to welcome you to this webinar titled The Art of Pitch Design and Pitch Development. During this webinar, we're going to cover a wide variety of topics, from simple physics of how a baseball moves to how we look to improve players' overall movement patterns. For those of you not interested in the physics part, I can only tell you that this is not meant to be a webinar on physics, but a basic knowledge of a few topics will help you understand the concepts much better. I should also say that we will not be discussing various topics such as velocity, spin rates, grips and seams, knuckleballs and splitters, and laminar flow. Here is a brief outline. As you can see, we will be covering a wide array of topics. So before I get into the webinar, I would like to say that this webinar is the result of a year's worth of work and analysis we have done here at RPP. Although there can be some areas of disagreement with others, we believe the contents here provide a true and tested summary of ball movement and what it takes to help understand and hopefully improve your movement pattern. In part 3, we cover various topics in some depth, including spin efficiency and spin axis, miscellaneous topics, understanding the Rapsodo, and some others. In part 4, we will show what it takes to improve movement patterns. We will discuss initial mapping, arm slots, miscellaneous suggestions, and then we'll have some closing comments at the end. I should also say that none of this would have been possible without the Rapsodo pitching camera system and their continued assistance in helping us parse through the data and streams of information coming out of it. The information can initially be overwhelming and seem complicated, but as you get into it and understand what it's telling you, it's quite amazing and interesting. The camera is a great piece of technology that will undoubtedly change how pitchers are evaluated and trained for years to come. So let's get started. The next several slides will talk about the basics of pitch movement. Everyone always talks about movement, but no one ever really gets into the how and why. If you ask most pitching coaches, why does a baseball move? You might get a variety of answers about the grip, the seams, arm slot, or arm action, but very few will actually talk about the ball itself and how it's really the spin on the ball that's creating the different types of movement. Many other things also contribute to it, but if you want to understand movement, you have to understand the spin on the ball. So let me explain in simple terms. A ball's movement is dictated by the imbalance of pressure created around it due to its spin characteristics. Every type of pitch creates different kinds of pressure around the ball. This pressure is called the Magnus force. Basically, a ball's movement is dictated by the laws of physics. Here's a diagram that demonstrates how the backspin on a typical fastball creates high pressure on the bottom and low pressure on the top of the baseball. This leads to what I had referred to as Magnus force. It's basically this force on the ball that's directing its movement. In this specific case, because of the upwards Magnus force, the ball will drop slower from the pull of gravity than it would have otherwise. We will get into this later, but obviously these movements could be up, down, and/or side to side. If you ask most coaches, movement versus what, I'm actually not sure what they'll say. So once again, in simple terms, there is this actual pitch that's thrown. This pitch moves to home plate with a certain pattern and its total amount of movement in its direct relation to a hypothetical pitch that has no movement. We refer to this hypothetical pitch with no movement as the gyro ball. So when we discuss movement, we are referring to change in the path of the ball from a hypothetical pitch that has no movement. Here is an example of an actual pitch in solid red line versus a gyro ball in the dotted red line. The dotted red line shows where the ball would have gone if there was no movement. The difference between the two pitches is the amount of movement on the ball, in this case shown by the dotted blue line. In this section, we're going to go over different types of spin. Now let's review more specifically how movement is generated. There are basically three different directions a ball can spin: along the x-axis, the y-axis, and the z-axis. Z being up and down, X referring to side, and Y in the direction between the pitcher and the catcher. Spin along each of these axes result in different directions of movement. Let's review each of these individually. Here we have spin along the z-axis. This type of spin leads to side or lateral movement on a baseball. A ball that spins to the left along the z-axis will move towards the left. This is basically due to the Magnus force we reviewed earlier. A ball that spins to the right will move to the right. This past year, for example, Trevor Bauer set out to create a new slider. He wanted only lateral movement and no vertical movement. During an interview, he said that he needed to have a pitch that spun around the z-axis as much as possible. He also went on to say that the more he can keep the axis upright, the more lateral movement he was going to get. More tilt means more Magnus force to push the ball sideways. Now he may have confused some people, but this is what he was talking about. He wanted to create a pitch that only spun like this spinning wheel, with its center spin axis pointing directly upwards. If a baseball spun like this, it would only move laterally, with no vertical lift. Let's see what he accomplished. Year over year, Bauer increased the lateral movement on his slider by over 5 inches, with a minor increase in the drop. That's a lot by any standard. Let's see how batters did against it. Batting average against the slider went from 195 in 2017 to 124 in 2018. To put it bluntly, a 70-point drop is pretty amazing. With that, hopefully, I got your attention. Pitch design and development using data can be extremely powerful. I certainly don't want to minimize the hard work Bauer put into doing this. Having pitched for years professionally, I know how hard this can be. But the results were amazing, and I want to make sure you appreciate the power behind this stuff. So let's move on. Here we have spin along the x-axis. This type of spin leads to up or down movement. For example, in order to throw a fastball, you want your fingers and your hand behind the ball when you release it. When you do this, your fingers are going to roll on the back of the ball and that will put backspin on it at the point of release. This backwards rotation causes the Magnus force to pull the ball upwards. While the force doesn't prevent gravity from ultimately bringing the ball back to the ground, it gives the fastball a little less fall during the flight to home plate. Here we have spin along the y-axis. This type of spin is similar to a spiral spin or football spin from the pitcher's viewpoint. This type of spin does not contribute to movement. We refer to this type of spin as gyro spin. Let me spend another couple more minutes on this because we refer to and discuss the gyro ball throughout this entire presentation. A quick word on gyro spin because it can get confusing. If you look at the image in the diagram, you will see red arrows pointing at a ball with gyrospin from all directions. These arrows represent equal and opposite air pressure that's created around the ball during this type of spin, which basically leads to a constant amount of pressure on all sides. As a result, this type of spin has no contribution to movement. Here's where things get interesting. Since only two types of spin contribute to movement, we look at these two differently. Together, horizontal and vertical spin create what we refer to as true spin. The relevance of all this is that pitches have different amounts of different types of spin, and it's important as we get into pitch development to know which spin does what. Just for clarity, I should also say that at times, true spin is also called useful spin or transverse spin by different people. I would like to spend the next few slides and go over what we call movement charts. This image is what I call a movement chart. Many people confuse this with a strike zone. This is not the strike zone. Let me say it again, this chart is not the strike zone. Dead center on this chart is the gyro ball, the black dot. As we reviewed earlier, this ball has no movement in any direction, and it serves as our reference point. Now let's talk about actual ball movement. On this chart, up and down we refer to as vertical break. Side to side we call horizontal break. Pitches above the horizontal line have backspin, like a fastball, in this case the red circle. Those below the horizontal line have topspin, like a curveball shown by the blue circle. Pitches on the left and right of the vertical line also have some degree of side spin. So for example, the red circle would be a typical fastball with backspin and some degree of lateral spin. The blue circle would be a typical curveball with topspin and some degree of lateral spin. Now that we have a good handle on movement charts, Let's put them side by side with the strike zone. In this slide, we kind of put it all together. Strike zone is on the left and the movement chart is on the right. It can get confusing, so let's go to the next slide to help explain how they relate to each other. Here we have the same slide as the prior slide, with two separate pitches overlaid on both charts. As you can see, the chart on the left shows where the balls cross the strike zone, but the one on the right demonstrates how the two pitches moved versus a gyro ball. Why is this all relevant? Well, after millennia, the human brain is used to objects moving in space following a set pattern, as in gravity's pull. Any deviation from that expected movement creates deception, and that's what gives pitchers the advantage. It's really that simple. Now let's discuss the concept of spin efficiency. You're going to hear this term quite a bit when we get to pitch design. Spin efficiency is basically the percentage of the total spin that contributes to movement of the ball. Previously, we covered three different types of spin. Think of spin efficiency percentage as the portion that helps the ball move, or simply true spin divided by total spin. Here is an example of a pitch with 85% spin efficiency. As you can see, 85% of the spin is what we call true spin, and 15% is spiral spin, which doesn't contribute to movement. Now that we know what creates movement, we can also say the higher the spin efficiency percentage, the more the movement. But this information is specific to the pitch. Higher doesn't mean better. It just depends on the type of pitch. Some pitches should be high like a fastball, generally north of 85%. Others should be low, like a slider, in the 20 to 30% range. Generally, the farther you go out in any direction from the center, or gyro ball, the higher the spin efficiency percentage and the higher the corresponding ball movement. Dead center is 0% spin efficiency, or what we call the gyro ball. Once again, this is the ball we compare all movement with. With spin efficiency behind us, now let's talk about the different factors that contribute to movement. A baseball's amount of break and direction of movement are a function of three topics: velocity, true spin, and spin axis. The first two, velocity and true spin, determine the amount of break. The third one, spin axis, determines the direction of break. We aren't going to discuss velocity much in this webinar, so let's move to number 2 on that list, true spin. Here's a chart for several hundred pitches we mapped with true spin rates on the y-axis and total linear inches of movement on the x-axis. As you can see, the higher the true spin on a pitch, the higher the total movement. Now let's talk about the third one on the list. Spin axis determines the direction of the break. Let me say that again because it's important and it's discussed in much of the rest of this webinar. Spin axis determines the direction of the break and the relationship is 100% correlated. So if you want to learn how to create different movements across various pitches, then it's probably a good idea to learn more about it. Let me first quickly cover what we mean by spin axis. I think this image is self-explanatory. We are looking at a typical fastball with backspin from a righty pitcher. As you can see, the direction of movement is up and in on a right-handed batter with this pitch. I am talking about the arrow pointing up. The arc on the top represents how we measure spin axis. During the rest of this presentation, we are going to discuss spin axis in great detail. The spin axis is often discussed and reviewed in terms of the minutes on a clock. For example, if we do a fastball at a 1 o'clock axis, it would be referring to a pitch that moved in this direction. Another example, if we do a curveball at a 7 o'clock axis, it would be moving in this direction. To simplify things a bit, I generally like to talk about the spin axis as kind of like the car's steering wheel. For most pitch types, think of the spin axis as the steering wheel. Whichever way it's tilted, that's the way the ball will go. We are now ready to get into movement patterns, as each type of pitch has its own general pattern. Here is an example of a typical movement chart that shows the movements on a 4-seam and 2-seam fastball. 4-seam is the purple circle and the 2-seam is the red circle. As an example, the fastball is up and in by approximately 9 inches vertically and 5 inches horizontally, versus a gyro ball at dead center. The chart is from a right-handed pitcher's viewpoint, and as you can see, both pitches move up and in on a righty batter, but the 2-seam has more lateral movement and less vertical. Most young pitchers' movement patterns look something similar to the chart on the left. Their movement isn't fully developed. The idea is to help pitchers improve and differentiate their relative ball movement among the various pitches similar to the chart on the right. The slide also highlights why certain pitchers are so successful in high school but begin to falter in college, as they face more advanced players. Here is a more advanced movement chart that shows the movements of a variety of pitches by MLB pitchers. The chart represents how an advanced professional pitcher would move the ball. As you can see, they move it quite well. Their pitches move all over the place as they create a good amount of relative movement among the different types of pitches. In a world of 100-mile-an-hour exit velos by hitters, this is why advanced pitchers are so successful. Be sure to follow us on social media, Twitter, Instagram, and Facebook at RPP_performance. That was the end of part 1. Let's go over to part 2 to continue this presentation.